Hello everybody, this is the second video associated with Chapter 4 of the Reinforcement Learning course. So in the first part of Chapter 4, we discussed dynamic programming algorithms, which were, for instance, the policy evaluation algorithm, where for a given policy pi, we wanted to calculate its associated state value function v pi. So we did that through an approximation scheme, a recursive scheme, which allowed us to obtain a sequence of functions which was said to converge to the optimal, to the value function v pi associated with policy pi. And then after that, we studied what we call policy improvement. So for a given policy pi, we saw how to construct a new policy pi prime, which improved on the previous one, and through this policy improvement approach, we discuss how to eventually have an algorithm converging to the optimal policy. Okay, so this is good because what we want to do is indeed finding that optimal policy for a given Markov decision problem. Okay, so now we will continue on this and expand a bit more on this topic. So first, in the first part of the chapter, we consider deterministic policies. Okay, so policies which assign a single possible action to a state. Okay, so the probability of taking some action in some state S is either 1 for the selected action or 0 otherwise. A quick note here on this slide is to say that this policy improvement theorem can be generalized to stochastic policies. Okay, so what can, sorry, I'm gonna skip to the next slide. What can happen here is that if we have two policies that are optimal, let's say one policy assigns action A1 in the state S, and the second policy assigns an action A2 in state S. Maybe both policies are optimal. So in that case, it's possible to assign like a non-trivial probability, so neither 0 or 1, to both actions to still yield another optimal policy. Okay, so when multiple actions are optimal, it's possible to pick one of them randomly through a given probability, and this is also an optimal policy. Okay, so the why I was saying that is that the previous policy improvement theorem we saw can be generalized to random policies instead of, or random or stochastic policies instead of only deterministic one. Okay, we won't go through the details of this, but I just wanted to let you know this. Okay, so we saw the proof for a deterministic policy, but again, these type of results can be generalized for stochastic policies. Okay, so if we recall in the previous part of the chapter, we came up with the idea or an approach to try to converge to the optimal policy. Okay, so the idea was the following. So we can start with any policy pi 0. Then with policy pi 0, you can apply policy evaluation to obtain an approximation of the value function v pi 0. And then from the value function v pi 0, you can apply policy improvement. So from policy improvement, you can get a new policy pi 1, which is equal or better than policy pi 0. Then from that new policy pi 1, you can apply policy evaluation to find its value function, and then continue like this until you eventually converge to the optimal policy pi star, and then from that optimal policy pi star, you can obtain the optimal value function. Okay, so here, every time there's an arrow with an E, this denotes a policy evaluation, and every time there's an I, this denotes policy improvement. Okay, so by starting with any policy, you can go through a sequence of policy evaluation, policy improvement, policy evaluation, policy improvement, etc., until you converge to the optimal policy and the optimal value function. Okay, so as we mentioned earlier, every time you come up with a new policy, the new policy must be a strict improvement over the previous one, unless it is already optimal. Okay, so at the first time, your new policy doesn't change with respect to the previous one and the policy improvement, then it means you must have converged to the optimal policy. Okay, so one question we might ask ourselves is it possible, let's go back one slide, is it possible that this sequence here takes an infinite number of time to converge? Okay, is there an infinite number of policies that we could contemplate before reaching to the optimal one? Well, the answer is if we have a finite MDP, there's a finite number of states and a finite number of actions possible in each state. So the number of possible policies is finite. Okay, so in that case, because there's a finite number of policy, the previous sequence here must have a finite number of policy improvement steps. Okay, so you will converge to the optimal policy with a finite number of policy improvements. Okay, so this way of interchanging policy evaluations and policy improvement, this process is called policy iteration. Okay, so policy iteration is the procedure where you start with a policy and then alternate policy evaluation to get a new value function and then policy improvement to get a new policy out of this value function you just got in the previous step. For some problems, the policy iteration can converge surprisingly fast to the optimal policy. Okay, so you might think it would take a lot of time to converge, but for some problems, it can be surprising how fast this converge sometimes. Okay, but again, this is very dependent on the problem. For some other problems, it might take a lot of time to converge. Okay, so we said policy iteration involves interchanging. Policy iteration involves repeating policy evaluation, then policy improvement, evaluation, improvement, evaluation, improvement, etc. Okay, so what's the problem with that? The problem is each policy evaluation is in itself an infinite loop. Okay, so every time there's an arrow in an E with the previous picture we saw, this involves, again, every time an infinite number of iterations. Because recall that to do the policy evaluation, what we said earlier is you start with an estimate of the value function, v pi, and then, so not the true v pi, but an estimate of it. So you can start with an arbitrary estimate, and then we saw how to construct a sequence of functions which would converge to v pi. Okay, but this sequence of functions is infinite. So you only converge in the limit. So in practice, of course, you have to stop it after a finite number of times or of steps, but there can be many steps required before converging to the actual value function associated with some policy pi. So this might be problematic because, let's go back a few slides. If every time you go through a policy evaluation, it takes many iterations before having a decent estimate of the value function, this whole process will take a lot of time. Okay, because if this takes a lot of time, if this takes a lot of time, if this takes a lot of time, etc., it ends up taking a very large amount of time. Okay, so is there a solution to that? So the answer is yes. This is what we're going to see next through a procedure called value iteration. Okay, so let's discuss that. So in practice, we said that in the policy evaluation, you had to do an infinite number of iterations to converge to the true value function. So we said in practice, we have to stop short. We stop after a finite number of iterations. But then let's consider a special case where we do a single iteration in the policy evaluation. Okay, so we start at our current estimate of the value function. Then we do a single iteration of the policy evaluation, and then we stop there before going to the policy iteration, policy improvement. Okay, so this algorithm where you replace each policy evaluation by a single iteration of that policy evaluation, this procedure is called value iteration. Okay, so value iteration involves starting with some policy, then do a single iteration of policy evaluation, then go through policy improvement, then a single iteration of policy evaluation, then policy improvement, and etc. So if you do that, you might wonder, does this make sense to do that? Okay, because if you don't converge to the true value function, maybe what are you achieving then? What's the outcome of this procedure? So we're going to see that despite stopping at a single iteration of the policy evaluation, you will still, the whole policy iteration process will still converge to the true value function. Okay, so this is a remarkable result. Okay, so let's discuss that more formally. So in what follows, VI here will represent the approximation of the optimal state value function after the ith policy improvement. Okay, so VI, it's not an approximation to VPI, the value associated with the current estimated best policy. It's directly an estimate of the optimal value function in this case. Okay, so VI, so how does it work? You start with a policy pi 0, then do a single iteration of policy evaluation, then you get V1. Then from V1, you do policy improvement to get pi 1. And then from pi 1, you do another iteration of the policy evaluation to get V2, etc. And here we want to know what will happen asymptotically to that V when I converges to infinity. So as you go through an infinite number of iterations of the policy iteration. Okay, so before answering this question, let's formalize this procedure into an equation. Okay, so here we're going to show the formula which combines a single step of the policy evaluation and the policy improvement step. Okay, so to do this, our procedure will entail having that after I plus 1 iterations of the policy iteration procedure for the state S, the estimation of the optimal value function is given by the expectation of the reward of the next step plus gamma times the estimate of the value function at the next step, given here your current state is F, of course, but your action you're taking right now is pi I plus 1s. Okay, so here using this equality entails doing an iteration of the policy evaluation. Okay, so you take the current policy, pi I plus 1, the policy that was currently optimized, and then you apply its policy to try to refine your estimate of your value function. Okay, so this is policy evaluation. if you do that many times, so if you repeat that iteratively many times, this would be a formal policy evaluation which would converge to v pi I plus 1. And then with that, what is this new policy that is optimized, or the current optimized policy? It's simply, from the policy improvement step, the action among all actions possible in state S of the expected reward plus gamma vi st plus 1, so the value function at the next state. So here again, we don't have the optimal value function, but we can use our current estimate of the value function. So given your current state is S and your current action is A. So what this means here is that the policy we use for the policy evaluation is the one stemming from the policy improvement scheme, which involves taking the action among all action, which maximizes your expected estimated reward plus next value function. Okay, so again, this is an estimate. It's not the true value, but it's our current estimate. And this expectation, how do we write it? It's simply, so the maximum stays here, but the expectation, it's an expectation over all possible values of the next reward and the next state. So it's a sum across all possible next states and reward of the probability they happen given the current state S and the current action A times the value of what's in the expectation, which is the reward plus the discount factor, times the current estimate of the value function in the next state. Okay, so here, this equation here, this is called the value iteration procedure. Okay, so having this recursive algorithm to refine your estimate of the optimal value function is called value iteration, and we saw that this algorithm can be obtained by combining policy improvement to a single iteration of the policy evaluation. Okay. So again, just recalling what we just said, the value iteration can be represented as the combination of as an update rule, which involves combining a single step of the policy evaluation and a single policy improvement. Okay, so having a single iteration of the policy evaluation involves some form of truncation of the policy evaluation step. Okay, instead of having an infinite number of iterations to converge to your vpi, you only do one iteration. Yes, this is true. Okay, and again, in the previous scheme, since we never have the optimal value function, it involves replacing the optimal value function in the right side of the Bellman equation by our current estimate of the value function, and this substitution allows us to get our new estimate of the value function, vi plus 1. And again, this equation, let's go back one slide. This equation is for a single state, so if we want to come up with a new estimate of our value function, we have to repeat this update procedure for all states S. Okay, so this can be very large if the state space is super large. Okay, so theorem. Okay, before that, because of the Bellman equation, if ever our current estimate of the value function is v pi, then the new estimate of the value function will also be, not v pi, v star. The new estimate will also be v star. Okay, so if our estimate of the value function is already optimal, already perfect, okay, then our new estimate will also be perfect. Why is that the case? let's go back here. So if you replace vi here by v star, the Bellman equation simply states that this right side must be equal to v star s. So vi plus 1 s will be equal to v star s. Okay, so because of the Bellman equation, if you replace vi by v star, then you'll have also v star on the left side. So your estimate of the optimal value function will not change in that case. Okay, and theorem, this is the important result. It can be shown that for any v0, so any initial estimate of the value function, so here I haven't put that here, but if ever you have terminal states in an undiscounted task, so if your discount factor is 1 but you have some terminal states, v0 you should assign a value of 0 for these terminal states. Okay, so I forgot to mention it here, but similarly as we discussed before, when you have terminal states in your initial estimate, you should set the estimate of the value of these states to 0, which is in fact the true value of such states. Okay, so aside from that condition, for any v0, the sequence of functions here, vi's, which we obtain after an infinite number of this value iteration procedure, it converges to v star under very mild conditions. Okay, so these conditions, again, we won't discuss them in details during the course, but for those who read the more advanced material, this involves determining if what we call the Bellman operator is a contraction mapping. Okay, so if we have these type of conditions satisfied, then it can be shown that the value iteration procedure does converge to v star, the optimal value function. Very interesting result, because this allows us to uncover the optimal value function and at the same time the optimal policy. Okay, so in the original policy iteration, we interlocked policy evaluation, policy improvement, policy evaluation, policy improvement, etc. And every policy evaluation step required an infinite number of iterations, because we had to set up a sequence of v's which converge to v pi, where pi is the current estimate of the optimal policy. Okay, so we replace this infinite number of iteration with the value iteration procedure, where instead we have a single iteration in the policy evaluation. In practice, we can do something in between. So instead of having a single iteration of the policy evaluation, it's possible to go through a few ones and then alter before going back to policy improvements. Okay, so in practice, what you can do, you could do a few steps or a few iterations of policy evaluation, then policy improvement, then a few iterations of policy evaluation, then policy improvement, etc. And sometimes this allows obtaining faster convergence for some problems. Okay, so this is an approach that is used in practice. Instead of having one or an infinite number of iterations in the policy evaluation, you can have an intermediate number. Say, let's say maybe 10 iterations or something like that. Okay, and how many? So we can say we can have an intermediate number of iterations in the policy evaluation, but how many of them should we have? Well, sometimes it's through a trial and error. You can determine that, but you can also determine some criterion, as we've discussed before, where you set a predetermined tolerance parameter and you stop the policy evaluation procedure when the movement of the estimated value function does not vary beyond your tolerance level. And all these intermediate schemes where you have an intermediate number of policy iteration schemes, policy evaluation schemes within your policy iteration, they can still be shown to converge once again to the optimal value function. Okay, so either if you use an infinite number of iterations, a single iteration, or a few iterations in your policy improvement within the whole policy iteration scheme, then you will still converge to the optimal value function. Okay, so are we done? So it seems we've found a suitable way to obtain a procedure which will converge to the optimal policy and the optimal value function. So we might say, well, we're done, we can stop here, we've solved our problem. But is there a problem with that? The answer is yes. So if the number of states is not very large, there might be no problem. Okay? And again, we must recall that here in this chapter, we assume the transition function p is known. Okay, so again, if p is unknown in practice, we have a first problem, but let's assume for now that we know that transition function p. There are still some problems with the policy iteration procedure outlined here. And the problem is still with, well, it's with both the policy evaluation and policy improvement. And the reason is that if we have a very large number of states, then even a single iteration of the policy evaluation or a single iteration of the policy improvement can be extremely long. Okay, so let's go back a few slides here. We said that, okay, so this is the value iteration scheme. Okay, we'll illustrate that with the value iteration, but this also holds for the regular policy evaluation or the policy improvements. Okay, so we said that to do that, to apply what we just discussed, we must apply this recursive equation, value iteration, for all states S. But if the number of states is very, very large, applying this single value iteration will take way too much time. Okay, so let's give an example here, which should strike your mind. So let's say we consider the game of backgammon, which has over 10 to the power 20 states. So if we are able to update the value of a state S at the rate of 1,000,000 states per second, then going through all of such states would take over 1,000 years to complete a single sweep. And by sweep, it's going through all the states once. So of course, then this becomes not feasible in practice. This is, it wouldn't be appropriate to have something requiring 1,000 years running. So in that case, we have to rely to something else. Okay, so when the number of states is too large and it's impossible to do a single sweep of the states, so to go exactly through all the states to do either your value iteration or policy evaluation or policy improvement, then you have to rely on something else. So there was another category or family of algorithms that were developed in dynamic programming to handle this situation, and this is called asynchronous dynamic programming. Okay, so how do they work? Asynchronous dynamic programming algorithms are, again, iterative algorithms, as we've seen earlier. So, but the difference is that instead of going through all states to do a sweep of all states, you will randomly select, either randomly or you can choose a few states to update in each sweep. So instead of sweeping through all the states and update all of them, you might pick a few of them at each iteration and only update these states. So in this procedure, it might happen that some of states are updated a few times before some other state is updated. Okay, because since you pick a subset of states, you might like the ones you pick for each iteration. Let's say you have states A, B, C. Then maybe in iteration 1 you update only A. Then in iteration 2 you update A and B, and then only in iteration you update C. The third iteration you update C. So it's possible that before updating C, you've updated A, for example, 2 times. Okay, so in that case, some states might be updated more frequently than others. So how do you select at each iterations the set of states that you update? Well, this is a good question. There are many possible ways to do that. Okay, so a good idea is to spend more time on states that are often encountered. Okay, so you want to be more precise to determine the value of states which you will often face. Okay, but now the question we might ask ourselves is, if we only update some of the states, do we still have the eventual convergence of our estimate of the value function to the true optimal value function? The answer is yes, if some condition is respected. And what is this condition? This condition is written here. So this condition says that to ensure convergence of the policy iteration scheme we've discussed earlier, where each of the policy evaluation is replaced by an alternative approach where you only update some of the states, then this whole procedure will converge to the true value function, provided that all states are eventually updated an infinite number of times. Okay, so you cannot say, for example, if there are states A, B, and C, you cannot say I'm going to update only A and B all the time and never update C. Okay, so if you do that, you might have a wrong estimate of C and you will never correct it. So in this case, of course, there's no guarantee that you will converge to the optimal value function. However, under again some mild conditions, although in each iteration you don't update the value of all states, if you pick a few of them, but across all iterations you eventually end up picking all of the states at not only a finite number of times, but if across all your iterations each state is picked an infinite number of times, as your iterations goes to infinity, then you still get assurance of your estimate of the value function converging to the optimal one. Okay, so this is great news. It shows that it's possible to not have to go through all states in each iteration of the policy iteration scheme. You can only update some of the value and policy for some of the states. Okay, so one specific case of this asynchronous dynamic programming is where you update a single state at a time. Okay, so here let's recall the value iteration procedure. Okay, so if we recall previously, in the value iteration procedure, at every iteration, you had to go through here. This first guy had to be equal to this first guy here for all states S. So the value iteration procedure entails that your next estimate of the optimal value function for some state S must be equal to the maximum across all actions. So why this maximum is to do it's a policy improvement, so you pick the best possible action of the next reward plus the discounted next value function of the next state. So here this is your current estimate of the value function weighted by the probabilities of each respective next state and reward. Okay, so here this is equal to this first line. This was the value iteration, but for value iteration you had to do that for all states. So now for asynchronous dynamic programming, we said we can do that for a subset of states, but we can consider the particular case where we pick a single state on each update. Okay, so if we pick a single state, then we can have a following sequence. So let's say we have a sequence of state Si, I goes from 0 to infinity, and assume that this sequence of state have the property that each state appear infinitely often in that sequence. Okay, so if you follow this sequence of states, you will eventually go through all states an infinite number of times. So what you can do instead, you can apply the value iteration update algorithm, but only for state Si at iteration I. Okay, so at iteration I, if your current state is Si, then you can update its value according to the same formula than in the value iteration. But for all other states that are different than Si, you keep your current estimate. So this means that you only update your value function estimate for a single state, and for all other states you keep the same estimate than in the previous iteration. Okay, so this is a limiting case of the asynchronous dynamic programming where you update a single state at a time. Of course, you can have other schemes where you update multiple states instead of one, but this is one particular case. Okay, so again, you might wonder what is happening in that case. So, okay, maybe I was a bit incorrect previously. Okay, so I jumped a bit too fast to the conclusion. So it can be shown. So you can refer to the textbook, which gives references for these results. It can be shown that if you have a discounted task, then using this asynchronous dynamic programming approach, where you do the value iteration, but by updating a single state at each iteration, if you have a discount factor smaller than 1, then you're guaranteed to have an estimate converging to the true optimal state value function. Okay, and again, this is assuming that we have the following condition, assuming that you go through each state an infinite number of times eventually. However, so this I wasn't exact because I didn't tell you that previously, but if you have an episodic case that is undiscounted, you can kind of build specific examples where you will never converge to the optimal value function. Okay, so it's possible to kind of trick the system and provide it with counter examples where your asynchronous dynamic programming will never converge if you have no discount factors. But however, there are ways to prevent this. So there are approaches to ensure that you will never face this problem. So you can find ways to select the sequence of states to avoid this problem. Okay. However, I don't necessarily want to go in these fine details here. So I just wanted to let you know that if you have an undiscounted reward case with an episodic task, then you might, in theory, run into some problems with that. Okay, but in practice, it's very atypical that you'll have problems. Okay. So, as we mentioned earlier, it's possible to intermix asynchronous policy evaluation and this should be policy iteration. Okay, so sorry about that. But it's possible to kind of intermix asynchronous policy evaluation and policy improvement updates to get new procedures. So again, instead of in our policy iteration scheme, you could have one step of asynchronous policy evaluation combined with one policy improvement, then another asynchronous policy evaluation step combined through policy improvement, and etc. And then, unless you face the technical problems we discussed in the previous slides, in most cases you should get convergence to the optimal value function. Okay, so this could be some form of asynchronous truncated policy iteration. Okay, so you still go through policy iteration, but in your policy evaluations, instead of having an infinite number of iterations, you have a single iteration or maybe a few of them, and each of these iterations, instead of sweeping through all states, you might sweep through a small number of states to avoid being locked into an endless sweep, which is too long if you have too many states. Okay, so again, this is the idea. We won't provide formal proofs for that. We leave technical details out of scope, because you could have classes solely dedicated to proving these things, but this is not the purpose of the current course, where we want to illustrate a broader like a broader set of methods. Okay, so we'll leave technical details aside, but this gives you a good idea of how to proceed in practice to use dynamic programming for to identify the optimal policy associated with some Markov decision process. Okay, so again, what is the advantage of using asynchronous dynamic programming? Well, the main advantage is if the number of states is too large, every time you do a sweep within your policy evaluation, you don't have to go through all of the states, you only have to go through some of the states. So your sweep does not take like 10 million years, it's going to take a few seconds instead. Okay, so it's more realistic. And furthermore, we said that there are many ways we can select the sequence of set of states which are updated at every iteration. Okay, so we said that the only condition we needed is that all the states are eventually sampled infinitely often to obtain convergence, but we did not provide additional details about how to select that sequence. So in practice, as we mentioned, a good practice in practice, yeah, sorry for that, but a good approach in practice is to spend more time updating the value or estimated value of states which are more important, and by more important, I mean that are faced more often in the application of your algorithm. Okay, so if there's a weird state that you never encounter and you don't care much about, it's not very important to update its value frequently typically. Okay, so for example, if you play chess and you have a weird configuration of the pieces that you'll never face in practice, well, why bother having a good estimate of the value of this state and the policy in this state, because we don't we practically are sure never to go there. Okay, so it's good to spend more time updating states that are faced more often in practice. And another thing that's positive about asynchronous dynamic programming is it combines very well with real-time interaction. So what do we mean by that? So again, let's go back to the case where we do asynchronous dynamic programming, and at each iteration we select a single state to be updated. Well, what you could do if you want real-time interaction, you can interact with your environment. So let's say you're trying to teach a robot how to walk. Well, you can have the robot try walking, and then every time you face a state, or maybe, okay, let's do tic-tac-toe or chess instead of a robot. Okay, so let's say you play chess against an actual opponent, and every time your opponent plays, then you play and your opponent plays, you get into a new state, and then you can use that state to be updated. Okay, so you can choose the sequence of states to be updated as the actual states you experience as you interact with your environment. Okay, so again, why would you want to do that? What's the benefit of that? As we mentioned, it's that when you interact with the states, and if you update states that are encountered, this will force you to update more often states that are encountered more often and which are more important. Okay, so this is what we mentioned earlier. So we should update states which are faced more often, and if you select the states to be updated by interacting with your environment, you will naturally determine what are these important states and will update them more often. So this is a possibility to apply asynchronous dynamic programming in a real-time setting where you interact with the environment. So again, like focusing on the most important states faced more often in practice, this is a recurring theme or idea in reinforcement learning. So we're going to see that we will come back to that later on when we introduce formal reinforcement learning algorithms. Okay, so right now we're going to summarize the overall idea from this chapter. So in this chapter, we saw an algorithm called policy iteration. So this policy iteration, it entailed having a process which intermixed policy evaluation, policy improvement, policy evaluation, policy improvement, policy evaluation, policy improvement, etc. So the policy evaluation, what it does, this is the first point here, the policy evaluation tries to take your current estimate of the value function and make it consistent with your current policy estimate, which means that you want to get a better estimate of the value function of your current policy or current policy estimate. Conversely, the other part of the policy iteration is policy improvement. So by doing that, you want to improve on your policy, and you do that by making a new policy that is greedy with respect to the current value function estimate. And what do we mean by greedy? We mean that it takes the action which seems to have the highest value according to your current estimate of the value function. Okay, so in the original policy iteration scheme, each of these processes, each of these steps, must complete before the other begins. Okay, so in the original policy iteration scheme, you go through a full policy evaluation, which would in theory require an infinite number of steps, and then you do a full policy iteration, then full policy evaluation, then full policy improvement. So full policy evaluation, full policy improvement, full policy evaluation, full policy improvement. But we just saw that this isn't necessary, because in practice you might have too many states to go through, and again, each of these steps, policy evaluation steps, they require in theory an infinite number of iterations. So in practice, it's unrealistic to have an infinite number of iterations. So we saw various ways we could truncate all these steps. So the first way to truncate is to replace the full policy evaluation with an infinite number of iterations by a single iteration of the policy evaluation. Okay, so replacing the infinite number of iterations by a single iteration, this allowed us to create a new algorithm which was called value iteration. But again, applying value iteration for some problems, it's impossible if the number of states is too large, because even if you have a single iteration of the policy evaluation, that iteration entails going through all of the states. So having to go through a sweep of all states, and this sweep, if you have, for example, in backgammon, something like 10 to the power 20 states, it would take way too much time to go through all states. So again, you have asynchronous dynamic programming, which can save you in that case. And instead of sweeping through all states, you could select at each iteration a few of the states, so a subset of the states to update instead of all the states. So this makes your policy evaluation iteration feasible in practice when the number of states is too large. Okay, and we saw that as long as we eventually update all states, even if it's not in each iteration all states are updated, but if the various states are updated infinitely often in the various iterations, then you can still obtain results which guarantee that your estimate of the optimal value function will ultimately converge to the true optimal value function. Okay, so this gives us a recipe to obtain the true optimal value function in the Markov decision problem. And along with the optimal value function, you do identify eventually the optimal policy. Okay, so this gives us a way to solve a Markov decision problem in practice. Okay, so we're going to use the term generalized policy iteration, written GPI, to refer to the general idea of interchanging truncated policy evaluation and policy improvements. Okay, so the original scheme, which we call policy iteration, entailed going through a full policy evaluation, then policy improvement, then full policy evaluation, etc. So this is policy iteration, but when we truncate the policy evaluation part, either through a finite number of iterations or through choosing a subset of states to be updated, we're instead going to refer to this new process as GPI, Generalized Policy Evaluation, where instead you interchange like your modified policy evaluation, truncated policy evaluation with policy improvement, with truncated policy evaluation with policy improvement, etc. So we're going to see later on that a very large number of algorithms in reinforcement learning can be very well understood by understanding the generalized policy iteration. Okay, so many reinforcement learning algorithms, they have identifiable policies, which are kind of current estimates of the optimal policy, and also current estimates of the value function. And again, in reinforcement learning, you constantly have this idea of trying to improve your current policy with respect to your current estimate of the value function, and always try to drive back your current estimate of the value function to your current estimate of the optimal policy. Okay, so this process here where you constantly try to improve your policy, and then after improve your policy, you try to refine your estimate of the value function to better match your new policy. This is also shared by reinforcement learning algorithms, similarly to what we saw in the generalized policy iteration. And exactly the same as we saw, if in this process, eventually your value function and your policy, they stabilize, and you're not able to improve on them anymore, then it means that you've reached optimality. So at some point, you know you are at or very close to the optimal value function and the optimal policy. Okay, so one last note about this. So in generalized policy iteration, you have two steps that are repeated many often, which are, again, evaluation of the policy and improving the policy. So evaluation and improvement. And they can be seen as both competing and cooperating. Okay, so why do we say they compete? It's because they kind of pull in opposite directions. So the policy improvement, it makes the policy greedy with respect to the value function you have. Okay, so by making it greedy, by altering your current policy, it makes your previous estimate of the value function inconsistent with your new policy. Of your new policy. Okay, so policy improvement makes your policy, your value function estimate inconsistent with your new policy because you alter your new policy to a more greedy one. Conversely, when you do policy evaluation, you refine your policy, your value function estimate to make it more consistent with your current estimate of the policy. But by making it more consistent, then your new policy becomes non-greedy with respect to your current estimate of the value function. Okay, so by making it non-greedy, this gives you more room to make it greedy again and then pursue on this generalized policy iteration process. Okay, so we say they compete in that way because they pull in opposite directions, but however, in the long run, we can say they cooperate because through these two processes, eventually you should converge to the optimal value function and the optimal policy. Okay, so this is great. This concludes this chapter. So in this chapter, we saw dynamic programming algorithms to identify the optimal policy and the optimal state value function associated with some Markov decision problem. So this is great. Some people stop there and say they solve Markov decision problems only with dynamic programming. However, what we'll do in subsequent chapters is to discuss what happens when it's not feasible to use dynamic programming because, for instance, we discussed these shortfalls. So sometimes the transition function P is unknown. So all the algorithms we saw here, if you check the recursions or formulas to update your value functions and policy, they all rely on that function P, the transition function. In practice, if it's unknown, then it's impossible to use dynamic programming, so you must use something else. Okay? There's also cases where the dynamics are not Markovian, so again, in these cases, you might face some problems, so it might be infeasible to use dynamic programming. And there are other problems where when the state space is too large. So again, this I will not go into details right now, but I'll just say that when the state space is very large, you can still do some things with dynamic programming. So dynamic programming can still be useful, but reinforcement learning that we're going to see subsequently is another possible route to handle this problem of very large state space. Okay, so we'll stop at there, and I'll see you next time for the next chapter where we will start introducing genuine reinforcement learning algorithms for Markov decision processes. All right, so have a nice day.